Hi guys, welcome to Science Chomp. Today is going to be interference part 2 and we're going to be specifically looking at calculations. So watch part 1 for the basics of the theory and all of that stuff. Today we're just going to be dealing with lambda is dx divided by L, where lambda is wavelength, d is the distance between the slits, x is the distance between the fringes, and L is the screen distance. And of course we also have this variation, m times lambda is xm times d divided by L. Okay, so let's first of all write them down over here so we don't mess them up. Here are the questions that we will be solving. Let's read question number 1 first. In a Young's double slit experiment, the screen is separated from a double slit source by 1.2 meters. The distance between the two slits is 0.03 millimeters. The second order bright fringe, m equals 2, is measured to be 4 centimeters from the center line. Determine the wavelength. Great. Now, immediately I can see they've got m equals 2, which means we require this equation rather than this one. So let's just write this out again. So m lambda is xmd divided by L. Now, fortunately for us, we don't need to actually worry about rearranging it because it says determine the wavelength, which is this one over here. So we can actually write 2 lambda, since m equals 2. Now, what's xm? Now, if you remember, x is the distance between the fringes, and they're saying the second order bright fringe is measured to be 4 centimeters from the center line. So this is going to be 4 centimeters. Now we can't just write 4. It has to be 4 times 10 to the minus 2, and that would account for the centimeters to meters. Okay, times d divided by L. What is d going to be? So d is the distance between the slits, and here it says distance between the two slits is 0.03 millimeters. So you have 0.03, and then since it's millimeters, it's times 10 to the minus 3, like so. And then L is the screen distance from the slits, and that's 1.2. I don't need to add anything because it's already in meters. Okay, so we've just got to solve this. So 2 lambda is going to be 1 times 10 to the minus 6, which means lambda is going to be 5 times 10 to the minus 7 meters, or you can say 500 nanometers. Let's have a look at our second question. A laser emits light of wavelength 500 nanometers. 9 orders of maxima separate points P and Q, which are 20 millimeters apart. The screen distance is 8 meters. Calculate the separation of the two slits. Okay, and again, because we've got 9 orders, we've got to have this situation over here, where m is 9. And because they're saying that we need to work out the separation of the two slits, we want to work out d. Okay, so you've got to rearrange this. So what happens is the L goes up there. So m lambda L divided by xm is going to be d. So let's work this out. So m is, according to our thing, it's 9. Lambda, the wavelength, is 500 nanometers. Now, nanometers is 10 to the power of minus 9, times L, which is the screen distance, that's 8 meters, divided by xm. Now, they're saying that this is the distance between the fringes, and it's 20 millimeters. That's 20 times 10 to the minus 3 equals d. So that gives us 1.8 times 10 to the minus 3 meters, and that is the same as 1.8 millimeters, because that would be the millibit. Thank you very much for watching. It's as simple as that. Like, share, subscribe, donate if you can. And if you look to the community bit, there's all sorts of weird and wonderful fun questions. Answer those if you can, and if you want another strange thing asked or answered, you can ask me there. Thank you very much, and goodbye.